Our last section in Chapter 3 is about exponential and logarithmic models. So we're going to be focusing more on word problems today. Now, we've talked about exponential growth, which we know is a graph, as a graph would look like this, 0, comma a, and it would go up, or a value 0, and it would rise rapidly and grow very quickly. Then we had our exponential decay model, which still had 0, comma a as our y-intercept. And this would go down like that and get, it would shrink very rapidly. And then we have logarithmic models. In our logarithmic model, for this, because our base is 10, 10 comma 0 would be the x-intercept, and our logarithmic model looks like this. It grows really fast at first, and then it levels out. So when we do these problems today, some of them will be exponential functions, some of them will be logarithmic functions. Now, we already did example number 1 in the notes from 3.4 part 1, so we're not going to spend any more time on that. So now example 2 talks about radioactive decay and how it can be modeled by this function here, c equals c naught times e raised to the kt power. So it kind of looks like that PERT formula, a equals p times e to the rt power. So we're going to use this formula for these problems. So it says, suppose the half-life of a radioactive decay substance is 1,620 years. If there was initially 10 grams of substance, how much is left after 1,000 years? So half-life, that's how long for there to for the radioactive compound to lower by 1/2. So it takes this long for 1/2 to remain. So if we start out with 10 grams in 1,620 years, we would lose half of that and go down to 5. Well, if another 1,620 years, we wouldn't lose 5 grams, we would lose half of 5, so we would be down to 2.5 grams. So we keep losing half of what we had every 1,620 years. So let's set this up. We have our t value for the half-life, 1,620 years, but we don't know what that k value is, so we need to find k first. So we need k. So we don't know what c is, but we know that if we have 1/2 of c naught, or the original amount, we could rewrite this as this right here. Because remember, this c naught is what we started with, and what we'll end up with is half of that after 1,620 years. So if we divide both sides by c naught, we get 1/2 equals e to the k times 1,620 power. Now remember when we did the PERT formulas, and if we wanted to double something, our shortcut would say 2 equals e to the rt power. So this is using that shortcut, but with half-life. Well, now that we have the base by itself, we can change this to a log. So log base e, or natural log of ln, equals 1,620 times k. So I'm going to divide 1,620 on both sides, and then in my calculator, I'm going to type this in with one step. So ln of 1/2 close parentheses, divided by 1,620, and we get a small number, negative 4.2786, e negative 4. So what that means is I move my decimal to the left 4 times. So I move it once, and then if I move it 3 more times, that means I'm going to have 3 more zeros. 1, 2, 3. So this is really equal to negative 0.00043. Now that we have that k value, we can go over here and say how much is going to be left after 1,000 years if I start out with 10. So C equals 10 times e to the kt power. Well, k we calculated was negative 0.00043 times 1,000. So I can type that into my calculator. 10 times e to the negative 0.00043 times 1,000. And we get 6.505. So C equals 6.505 grams. And since 1,000 years is less than its half-life, we know we should have more than 5, which is half of 10. Example 3, suppose the half-life of a radioactive decay substance is 5,700 years. If there is 1.2 grams of the substance after 1,000 years, what is the initial amount? So we still need that k value. So 1/2 equals e to the, this time is 5,700 times k power, because our half-life is 5,700. So then we're going to do the ln, or natural log, of 1/2 equals 5,700 times k. And when we divide both sides by 5,700, it's going to be a small number again. So the ln of 1/2 divided by 5,700, and we get the same thing. So we move the decimal left twice, or sorry, 4 times. So 1, 2, 3, 4. So it's going to be negative 0.00012. All right, so now we have our k value. All right, now over here, we don't know what the initial amount is, but we know we end with 1.2, and that's going to equal C naught, the initial amount, times E. Let me rewrite this a little bit neater. Times e to the k, so k is negative 0.00012 times t power. Well, we're trying to figure out after 1,000 years. So now in my calculator, I'm going to type in, just this part right here. E to the negative 0.00012 times 1,000 power, and we get 0.887. So 1.2 equals 0.887 times C naught. Divide both sides by 0.887. So 1.2 divided by 0.887, and we get 1.353 equals C naught. Now, we know that this is not exact because we rounded this k value over here, and we rounded some other numbers too. So if you're off by a few decimal places, don't be concerned with that. All right, now example 5 says find an exponential model y equals a times e to the bx that fits the points 0, 2 and 3, 10 on the graph. So we're going to use this y-intercept here because what that allows us to do is it lets us calculate our a value. Because we know that if I substitute 0 in for x, my y value is 2. So y, which is 2, is equal to a times e to the bx power. Well, x is 0 if I use the point 0, 2. We know that anything to the 0 power is 1. So 2 equals a times e to the 0 power because this b times 0 is 0. This is equal to 1. So 2 is equal to a. Now that we have our a value, we can figure out what that b value is using the other point, 3, 10. So y is 10. We now know a is 2. E, we don't know what b is, but we know that x is 3. Divide both sides by 2. 5 equals e to the 3b power. Now we have our base by itself, so we can change this to a log. Log base e ln of 5 equals 3b. Now we're going to type that into our calculator, ln of 5, and we're going to end up dividing both sides by 3. So I'll just do that in one step. B is equal to 0.536. So my model will be y equals 2e to the 0.536x power. That function has both of those points that lie on the graph. Right, so I hope that this lesson gave you some examples of when you would actually use logarithmic and exponential functions. So make sure to like the video and subscribe.